yeah, I'll let you look at the exercises a bit, and then I will start. So what we want is, we would like to give a proof of this theorem. So for any n-dimensional spherical Riemannian manifold, the systole is bounded by the volume. And you see, well, there is this constant here that depends on the dimension, but does not depend on the topological type of the manifold. Note that this is non-trivial, of course, even if you fix the manifold, but the constant only depends on the dimension. It doesn't depend on the manifold. And the way I would say it is that systole is bounded by the volume, because, of course, when you rescale the metric, as I said before, the systole is rescaled by lambda, the systole is multiplied by lambda, but the volume is multiplied by lambda to the n, right? So, of course, you need this 1 over n there, otherwise it doesn't make sense. Another way to think about it is you fix the volume of your manifold to be 1, and then you wonder whether the systole is bounded. So just forget about volume, say you only think about manifolds of volume 1.
Would you remind what is aspherical?
Right, thanks. So aspherical means that if I take f from Sn to m, then it is contractible. For n greater or equal to 2, then f is homotopic to the trivial map, right? To x, c, x0. The map that sends Sn to some point x0 in M.
Does it just mean that
every high dimensional sphere contracts.
So all homotopy groups.
All homotopy groups,
yeah.
Right, so it's, all homotopy groups are regular. Okay, so this is aspherical. Any other question? So, as I said before, we're talking about periodic geodesics, and this allows us to solve the problem of a spherical manifold, right, when the fundamental group is non-trivial, but it's still open whether there is such a bound for S3, and Crook's theorem that we saw before is that there is such a bound for S2, right, for the two spheres. Okay, so Gromov also gave this constant for his proof, and then later this was somewhat improved, I think, but I'm going to present a more recent proof by Nabutovsky, which gives that the constant is less than n. And so it's a vast improvement geometrically, and also the proof is simpler. Okay. Well, I won't actually quite prove this in this lecture. I mean, I will only manage to do 3n or something like that. But that's the theorem. And in fact, the theorem is a bit less than n. So, of course, as you see, the constant is to increase with dimension, right? And there are examples where it tells that the constant has to be bigger than square root n. So, higher dimensional tori. Volume 1, there are higher dimensional tori of volume 1 where the constant is greater than square root. Okay, but yeah, the optimal constant. Oops. Okay. Okay, we'll need the notion. Okay. We'll need the notion of Jurison width, and which actually comes from classical topology, from dimension theory, but it's very natural in geometry. So, because, okay, we have a manifold, but it might be degenerating, it might be looking like a manifold of a lower dimension. So, and the way to talk about this is to use Jurison width. So, just to give a simple example, I mean, here is a torus, and now think of a torus that looks like that, right? So, it's a small cube. Now this looks more like something of lower dimension, S1, right? And now we say that the space has more Jurison width if there is a map, so small q Jurison width, if there is a map to a q-dimensional complex F such that the pre-image of every point, so I take a point here, the pre-image here is small, it has small diameter, okay? So this is a way to formalize the idea that space, finite dimension could be close, could be look like something of, say, lower dimension. That's what we usually care about. So this is the formal definition. We have Q unison with less than W if there is a Q-dimensional simplicial complex, so we go, so if it can be approximated well, so to speak, by a Q-dimensional space and a continuous map, such that every fiber has dimension, has diameter at most W in X. Okay, so that's, and X, of course, I don't need it. I mean, I talked about manifold, but I don't need X to be manifold. X can be anything. But now it turns out for the proof gives a bit better constants to give radius, Q unison radius. So I will work with this variation. So here, instead of diameter, we ask that every fiber is contained in a ball of radius less or equal to R in X. Okay, so yes, it's the same picture, but now I take a point X and then P index of X is some set, and I ask that it is contained in a ball of radius Q. There is some X, doesn't have to be there, and this is the ball of radius R. Okay, so that's the picture. And I will use this notation. I will say that the radius of a set is less than R if it is contained in a ball of radius R. Okay, and now there are different ways to think of unison radius. I gave the definition, but now an equivalent way is to think in terms of covers. So a compact metric space has unison n radius, so now I change my Q to n. If and only if it admits a finite of cover with multiplicity at most n plus 1, such that the radius of every one of the sets is bounded by R. Okay?
Excuse me, what is multiplicity of cover?
Thank you. Multiplicity is the maximum, so I have a cover, so the multiplicity is max k such that there exists ui1 uik in my cover, let's call this u, such that the intersection of uij, say equals 1 to k, is non-trivial. Okay? So yeah, so if I have something like that, that's my cover, then the multiplicity is just 2.
Excuse me, may I ask why it is natural to test like diameter and radius of pre-images on CW complexes? Like,
Oh, I said, I mean, of course, a metric CW complex. Right? Did I call X? No, X was not a W complex. X is just a metric space, right?
okay.
So, yeah, I have in mind usually a manifold, right? That's what, but I just have a metric space, and I want to quantify how close it is to something n-dimensional, right? So my space could have a high dimension, right? But it might look, metrically, so it's this picture I drew of the torus, right? Even though it has whatever dimension it has, 100, it might look like one dimension, right? It might get closer and closer. So, for example, if it were degenerating, right? Maybe it's going to degenerate to something one-dimensional, and I would like to say, oh, it gets closer and closer to something one-dimensional, and the unison width is a practical way to quantify that. Maybe you can find another way, but this seems natural. Say for Gromov Hausdorff convergence or something like that. You can say, yeah, it's a strange notion, right? It's it comes from dimension theory, but if you're a geometer, I mean, after a while, it kind of appears natural, right? If you want to think of the manifold metrically, and not just topologically, but metrically, I think it's a natural notion, and we will see it does have some applications here. Okay, so let's try to prove this. So let's try to come up with the open cover. So let's assume that there is f s in the definition. Now I claim that I can find a fine open cover of Kn of multiplicity n plus 1. And then for this fine open cover, I haven't said how, right? I'm going to say that. But then for this fine open cover, I'm going to get that the radius is small. Okay, so my first goal is to get this fine. So you know what I know. Okay, maybe I should go back to this. So what I know is if I take a point, f inverse of x has small radius. So now I just want to replace my points like with open set. So what I claim is, oh, I can find, if I go sufficiently close, the inverse image of this open set will still be contained in a small ball, right? Which is not surprising, but I'm going to do it precisely. But yeah, I mean, if a point is small, well, if you just thicken it a bit, it should be small. So let's prove it. So how do we do fine? So f inverse of p is contained in an open ball, so x is compact here, right? So p of x minus b is compact, right? So maybe I'll do a picture. So I have p inverse f inverse of p, which is this, but it is contained in this ball, right? And now the complement, so this is an open ball, so this complement is compact. So I take its image, p, did I call it p? Sorry, this is wrong. Okay, that's why f, right? F is compact, and p, of course, doesn't, and p, yeah, okay, so this. There is no p there, and now I had a point here that was p. Okay, and now, so I take this f, so this is compact, so the image of this compact is a compact set, so it's something like that. Okay, so now I replace my point P by this UP. I should call it UP here. And now F inverse of this is contained here. Okay, so maybe I should have called it VP there, right? Okay, so I got my fine cover, so I managed to do that. I got a fine cover where the radius of each pre-image of an element of the cover is contained in a ball of radius r. Okay, right? So I managed to thicken my points, but now I appeal to classical dimension theory. Well, first of all, I can pass to finite cover. And now, since the dimension of this space is Kn, I can pass from this cover to a finite cover that has multiplicity n plus 1. So this just comes from dimension theory. If I have a finite cover, I can find a finite cover where the multiplicity is as expected by the dimension. Okay. So, by the way, yeah, this multiplicity is one way, I mean, this cover with a given multiplicity is one way to define the dimension of a space, of a metric space in general, right? So if we have a simplicial complex, we can define dimension, but in classical dimension theory, the way you define dimension for any, say, compact metric space is you say, for every epsilon, there is, so the dimension is less than n plus 1, if for every epsilon, there is an open cover with multiplicity at most n plus 1. There is a cover, sorry, where the diameters of the set are less than epsilon, the multiplicity is less than n plus 1. So this is a way to define the dimension of a metric space. Okay? So using covers and multiplicities. Anyway, so I proved one direction, right? I proved that if the unison radius is r, then there is this cover. And now I'm going to go and do the other direction. If there is this cover, then the unison radius is at most r. Okay, so that's what I want to prove. So now I take the net of the cover. Okay, so maybe I should remind what is this. So first of all, let me just simplify. I don't want, it doesn't matter much, but I don't want extra sets in my cover, right? So if a set is not necessary, I just throw it out. If the rest cover, so let's say that my X is compact, so I have a finite cover, I have thrown away the unnecessary sets. So for every UI, there is X that lies in UI and doesn't lie in UJ, right? Okay, otherwise I would have thrown this out. Okay, and now what is the nerve of a cover for every UI? Oh, let's see, what is the anyway? For every UI, I associate a vertex, right? So the nerve of a cover is a simplicial complex, right? So this is a simplicial complex. I don't remember if it has come up in a previous lecture. Define. And now, to define the simplicial complex, I have to define the simplices. So VI1, VIK is a simplex. If and only if lies in Kn, if and only if UI1 intersection UIK is non-empty. Okay, so this is the nerve of the cover. And we can, so every time we have a cover, I mean, we have seen partitions of unities probably for manifolds, but every time we have an open cover, we can get a partition of unity. And now I don't care about differentiability and smoothness. It just means that the sum of Fix is 1, and so just what is a partition of unity is a map like that, such that the sum of Fix is 1, and these are defined on these sets, and that the boundary of the set becomes 0. Okay, and now I want to really visualize this Kn. I mean, it is easier for defining my map to think of this Kn as lying in some R n, some so n big, as big. Remember, this Vi is a finite cover, right? So n equals, I don't know, the cardinality of the cover plus 1, something like that, some big. And I want to think of this Vi, so think of the Vi's for defining this map, so I'm still trying to make sense of this, of what I wrote. So think of Vi, which are the vertices of, so which are the vertices of K to the n, as basis elements. Yeah, you have an orthonormal basis in this, as distinct, of course. Basis elements of Rn. Okay, just take an orthonormal basis, and every one of the vertices just enter there. Well, then I can define my map simply by this formula, right? Where these are just vectors, and this is in Kn, which is contained in Rn. So think about this. These are just barycentric coordinates. Since the sum of Ix is 1, this just gives you something with symbols, okay? So this is clearly continuous, right? The phi are continuous. So I defined my map to complex, and and then when X doesn't lie in UI, of course this is 0. So the pre-image is well, no, I didn't need to say anything about the pre-image, right? I just okay. So now an observation that one can see from this is that Fx, if X lies in UI, f of X lies in the star of UI. So this is something that will be of some use later, to emphasize it. And you can see that because if I have X here in UI, well, first of all, maybe just to make a remark, before I said there is an element here that doesn't lie in any other, right? So this is just going to go to the basic element ui because it's going to have coefficient 1, right? But now if I take another point, well, it might lie to other sets, but if it lies to another set, so then it can have fix non-zero, but this other set intersects vi, right? So that means that the coefficient is non-zero if and only if, so let's call this uj, so fj of x is non-zero if and only if, if implies rather that uj intersection ui is non-trivial. Here, vj is adjacent to vi, okay? And this implies that f of x lies in the star of vi. So it's one of the simplices adjacent to this vertex. So maybe I'll draw a picture of the star. Yeah, sorry, I didn't define the star, but this is the star. It's just all simplices adjacent to this one. Okay, so this closed set is the star of vi. Is this. Okay, so we have now a reformulation of Jurison radius in terms of covers.
One question. If you don't assume compact, does they still hold? Or?
Well, okay, I didn't want to. I want to avoid compact because when you define Jurison weight, you have to work with proper maps. And yeah, so I haven't thought about. And then, yeah, I guess that there's technicality. It should work. I think it should work because you just have a compact exhaustion and you can define a term set and this is going to stabilize, right? So I think it works. It's just that the definition is not exactly the same, okay? You need proper maps when you define the Jurison width for non-compact spaces. Okay. And now, okay, so I said I'm going to prove this for spherical manifolds, but in fact I will work with more general objects than spherical manifolds, which are essential complexes. So the definition, I admit, might feel a bit obscure, but we'll see very soon that spherical manifolds are essential, at least, so something that is more natural. So an n-dimensional simplicial complex is essential if there is no continuous map, so F continuous, to the Eilenbach-MacLane space, to the KG1, such that F star is an isomorphism on the fundamental group, and F of xn is contained in the n-1 skeleton of this space. Okay? So it's a somewhat technical definition, and there are variations of this definition in the literature, but I think this is the one from Nabutovsky. Okay, so why this is natural, or at least let's see that an aspherical manifold is essential. Okay, in this case, this space is just simply the manifold, right? Because it is aspherical. This is basically an aspherical space with fundamental group this one, and this is an aspherical space with this fundamental group. And now, let's say that we have F from Mn to Mn minus 1 inducing isomorphism on pi 1. Okay, well, but then since I got an isomorphism, I can get G back from Mn minus 1 to Mn, such that this composition is identity on pi 1. Okay? Now, if you have a map from Mn to Mn, let's call it H, such that H star is identity on pi 1, then H is homotopy equivalent. So this is because Mn is aspherical. So Mn aspherical then this is homotopy equivalence. So is homotopic to identity, sorry. So then this is homotopic to the identity map. Okay? So this map is homotopic to the identity. But now I claim this is a contradiction, right? So if we believe that, maybe I'll go back and say something about this. So theorem. So this is classical. Now, why this is a contradiction? Well, because now I look what this map does on homology, right? So this also induces a map. I don't know how to do it. I will just say the same. From Hn of a man to Hn of a man, right? Okay, and since it's homotopic to the identity, it sends the fundamental class, right? So this is non-zero, the fundamental class to the manifold to the fundamental class of the manifold. But that's not possible because when we took G, when we took F, we sent the fundamental class to something lower dimension, so we killed it, right? Okay? We already killed the fundamental class, we want something lower dimension. There is no way to resurrect it. Okay, yes?
Do we work with orientable manifolds? Or why do fundamental classes exist?
Oh, okay, yeah, actually, I mean, as I said before, for the systole, actually, yeah, I should have said oriental.
You could take the two coefficients.
Yeah, I could take the two coefficients too, right? Yeah. I mean, yeah, thanks, actually, the two coefficients are fine for this. As I said before, anyway, yeah, I mean, we can always think oriental because if you pass to the double cover, and one happens to the systole. But there is, yes, let's just take the two coefficients. Any other question? Yeah?
Is there a simple example of a non-essential manifold?
Non-essential manifold. Yeah, well, of course, I mean,
Okay.
S2, right? Yeah, I mean, I will just take S2. So S2, well,
Non-simply connected, so that there is no so that there is a systole.
well, S2 times something.
Okay.
Yeah, I mean, it's essential is clear to aspherical, but there are some essentials like RP infinity. I mean, there are RP is essential, but it's not aspherical. So it's encompasses a slightly bigger class. But any more questions? Yeah, I don't know if I'm going fast or slow because with this I can just click. So I'm just waiting. So maybe I remind you quickly why if we have an spherical manifold and we have a map that induces identity in pi 1, right? So let's say I have F and well, let's call it H, and then H star identity in pi 1. Okay, I want to show that there is F, the homotopy, Mn times I, so spherical, to a man, which from the identity, right, from identity H. Okay, so what is the idea? Well, first of all, let's think of it as a simplicial complex, and let's construct a maximal tree. So we can just simply assume that we have a cell subdivision with only one vertex, right? So we have only one vertex, and so F, and we can assume that H and the identity, of course, just both map this vertex to itself, right? So maybe we'll draw the picture. So we have this vertex, and then H and the identity map it to itself, right? And now I'm going to take a loop, right, in the one skeleton. So I had N and 0 was just this V, and now I'm looking at the one skeleton. So I have a loop, right? But and now I want to find a homotopy. So I have the image of this H of alpha, and I want to but now I know that H is homotopic to the identity, so there is a homotopy between this loop and this loop, right? So, so I can extend my homotopy. So using this, I can extend now. So my map here to the two skeleton. Right? I can extend my homotopy to the two skeleton. But now the fact that Mn is aspherical tells me that I can extend to all the other skeleton because there are no spheres of higher dimension. Okay? So I can extend this homotopy to all dimensions, and that's basically the proof. And if you have more than one vertex, well, again, we can just adjust the map so that it sends everything to a single vertex. Okay, so and now let's see how this relates to Jurison width. So why did I do all this? If Sn is an essential polyhedral space, then the systole is bounded by either the Jurison width or the Jurison radius. And in fact, Karasev proved two, but I'm just going to do some more concrete proof, and I will sacrifice the constant, but the actual. So this theorem was proven by Gromov earlier using the filling radius, but this is a nicer proof. It's very recent actually, because it is direct, right? It doesn't. It's just an elementary proof. These two geometric quantities, the systole and the Jurison radius or Jurison width, well, are related, right? The systole is bounded by the Jurison radius. So this, yeah, we see an application now, at least of this strange notion, right? It bounds the system. Okay, so let's take a cover. As in the definition, each UI is contained in a ball. And now, if alpha is a loop, so now we want to see, how big can the systole be, right? So now we assume we argue by contradictions here. So we assume, I assume throughout, that the systole of Xn is bigger than 6 units in radius, okay? Okay, and now if I take a loop, I can write it like that as a concatenation, so I have my loop. Well, of course, this writing is not unique, right? But and in fact, for most of the time, so to speak, my arcs are contained in an intersection of two. Okay, so because you see, I mean, I'm going to shortly look at the map, right, of this. So I have R1 and so on. I'm going to look at my previous map to a simplicial complex, right, and see if a part of the arc lies only in one and no other, then this whole part, because of the way I defined my map, right, using partitions of unity, this whole part is going just to go to a vertex, right? And then we have this other arc that is going to go somewhere, and then if it ends up being for a while in a single set, again, it just goes to a vertex. So this is a picture, and this is my alpha 1. Okay, so certainly I can do that. So I am perhaps in only one set. As soon as I meet the second set, I follow it and I say, okay, now I'm in this set. I'm in U1, U2. When I get out of U1, I'm in U2 and perhaps another set, right? And I continue. Okay, and now let's see. Okay, so I have my map, I have alpha, and I want to see if alpha. So what I want to show is that the map whether the map I defined before from the complex from Xn. Okay, yeah, one I want to show. So what I'm after is I want to show that the map that I defined before, f from Xn to k from to kn minus 1, sorry, kn minus 1, sorry, here I'm talking about n minus 1 derivative, right? So what I'm after is I want to show that this map actually is injective in y1, right? Because that's why I'm looking at loops. So I look at a loop, and now I claim, first of all, that alpha is homotopic to the piecewise geodesic loop with these vertices, the centers of the corresponding balls for my sets UI. So maybe I'll draw a picture. Okay, so let's see. Where is this? Okay, U1, U2, and these are contained in some balls, right? And I have the center of the first ball, P1, P2, these balls, and I have my arc here. U by alpha 1. Right? And now what I know is that this is less than R, and this is less than R, right? But I can go on, so now I can create small loops here, small loops, so all have distance roughly 2R, have length roughly 2R, so if I go up to here, I have a homotopy, so up to the middle where both intersect, I have a homotopy, and up to here, I have a homotopy, right? So, so this part, I mean, I'm going to use free homotopics throughout. So this part, I can just homotope alpha 1, I just homotope to this green arc, right? So there is a homotopy to this green arc. Here. Okay, but I said I want to replace it with the geodesic, with the piecewise geodesic arc. Well, now if I take the geodesic, well, the distance between these two is at most 2R, right? So I have something that has overall length less than 4R, right? So since the systole is greater than 6R, these two are also homotopy, right? So I created a homotopy going from this. So this is kind of a free homotopy, but as you see, I'm going to do it in all sub-arcs now, right? And then the whole. So I can think of this original arc I had. I can replace it by a piecewise geodesic arc that instead of going from open set to open set, it goes from the center of the balls to the center of the ball and so on. So I replaced my loop by this piecewise geodesic loop. So it is homotopic to this new loop. Okay, but this didn't do yet anything for me, right? So what I care about is what is the image of this in kn minus 1. I want to show that this is non-trivial. Okay. Or if it is trivial there, it is, I want to show that this map is 1 to 1. So let's try to understand the image of this in kn minus 1. Okay, so now I have my map, and I want to see what happens to my loop. Okay. Okay, so I'm not going to use actually this. I write for emphasis, but I'm just going to look at alpha again to see what happens. What is it homotopic to, right? So as I said before, well, maybe the beginning of alpha, and it could be that it could be or it could not be that V1, V2. So the picture could be like that, and perhaps part of it lies, most likely not, right? But perhaps of it lies only in V1 and not only in V2. So this is next to. So it could go like that, but what really happens, I mean, if it lies only in the U1 or U2, it just goes to a single vertex, so nothing happens. So, so when the arc really becomes an arc, is in this common region. Okay, but all these points lie both in U1 and U2. And as we said before, if you lie in U1, that means you are in the star of U1. And if you lie in U2, that means you are in the image, you are in the star of V1 and of V2. So this whole arc, so f of let's call this, I don't know, beta. So f of beta is contained in a star of V1 in the section star of V2. So it could, so that means it lies in a simplex, right? Which has its vertices both V1 and V2. This is where, I mean, maybe higher dimensional simplex. So there are 2 dimensions, but maybe. So this is where f of beta lies. Okay, so then I can use a homotopy there to push it to V1, V2. So I can replace, because the simplex is, of course, contractible. So, okay, so I can push it to the boundary. Okay, so what did I get? So first I said when I'm in X, I can replace alpha with P1 pk, and when I'm in the image, I can replace it by a sequence of vertices, right? So it's homotopic to a sequence of vertices. Okay, so I should have done this in 2 steps, but let's say that the image is equal to the identity. Well, remember, the image is simply an arc that we get by a sequence of vertices, right? And since K is a simplicial complex, if a loop is trivial, then there is a simplicial homotopy. So how do simplicial homotopies work? You just have 2 vertices, V1, V2, V3, and 2 edges, and then you replace this by this, right? That's how the simplicial homotopy works. Okay? Okay, so then we have a recipe for a simplicial homotopy. But then now, where Vi, Vj, Vs, of course, are adjacent. But now, this simplicial homotopy, I claim I can imitate, I can run also on this loop now. So now I go back to the pre-image and I look at this, right? So if I have this there, then I have Pi, Pj, Ps in the path homotopy to mine where all these are actually adjacent. And so since they are adjacent, this is less than 2r, this is less than 2r. And so here I had the simplex, here I have nothing for the time being, but what I have is that all these are adjacent, so this is less than 2r too, right? Oh, okay, but the systole is bigger than 6r, so there is a homotopy from this to this. So the simplicial homotopy in the image gives me a homotopy also in the space, right? So this is 1 to 1. Okay, is that clear? Sorry.
So what have we proved? So we have proved that this...
I proved that this map, okay, so this is something, that is not clear, right? I had a map from Xn to a lower dimensional complex, but I don't know if it is 1 to 1 on the pi.
Okay, so that's what I proved.
So, yeah, what I proved is 1 to 1. But the same argument, actually, just imitating, you can see easily that I can also show it is an isomorphism, because every path in the image I can also do in the space. So this, there is also another way to get around this, but okay, so it's an isomorphism. Oh, okay, but that contradicts essentiality because I managed to send this. Okay, maybe I will. Right, so I proved. Any questions, first of all, about this proof?
So could you repeat again? So why? So in the domain you have a homotopy of alpha into this P1 to Pk, and then how do you show that the image is not contractible?
Right. So let's assume it is contractible. Well, I need 2 things, right? First, I have P1, Pn in my original space, but now in the image, I also have the corresponding points. So U1 has 2 points associated to it, right? So if I have a set U1 in the space, well, it's contained in some ball, maybe a ball like that. So U1 is associated to this P1, right? But it has a point that doesn't lie to anything else, and this is which maps to the point X, to the point V1 there. Okay, so there is this correspondence. So when I map F, this is how I define my map capital F from my space to the simplicial complex Kn minus 1. Okay. So what I showed 2 things. I showed that the loop itself is, so the loop alpha is homotopic to P1, P2, P3, and so on, Pn. But then I also showed that f of alpha is homotopic to this edge path which is V1, V2, so the same V1, V2, Vn, right? I mean, the same corresponding points, right? So in both in the space and in the image, the loop is corresponding to the natural thing that you would want to associate to it. And now I look here. So my problem is, oh, maybe this is trivial. So I want to show if the image is trivial, then alpha was trivial too. Okay, that's what I want to show. So I say, okay, if this is trivial, that means that there is a simplicial homotopy, right? Because I'm a simplicial complex. So I know that there is a simplicial homotopy, so I can start contracting it like that. Okay? So there is a simplex there, and then another simplex. I don't know how it goes, the simplicial homotopy, but there is the simplicial homotopy. Okay? Oh, but now I go back and say, oh, there is a simplicial homotopy. What does this mean? It means all these vertices are next to each other, right? So that means that all these P1, P2, P3 are at distance less than 2r. That's what I know. That's obvious, right? If you have to intersect, it says the P1, P2 are at distance at most 2r. Okay? But then I can take also this, because P1, P3 are also close to each other. So this is also less than 2r. Okay? So this means, since this is smaller than the systole, that there is a homotopy here in the space. Okay? Yeah. It's quite basic lemma, so I don't mind staying a bit here, right? And it's a nice lemma because, of course, in general, I mean, if you take the map from a set to the nerve of a cover, there's no reason to be, so let's take this example just to see what we're doing here. If I have this cover of S1, so I take this, and then I take this, then the nerve of this cover is just an interval, right? So this map is not, right? So, of course, it doesn't my properties, but the map is not necessarily injected. Okay, so I get an isomorphism here, as I said, I filled up with the same thing shows on top, and now I can map this back to the to KG1, and I have that so this is simplicial complex, so I can map it to a simplicial complex of the same dimension or lower going back. So I get a contradiction to the essentiality. Okay, because I'm going through a lower dimensional space. Okay, this contradicts my hypothesis that the space was essential. Any questions? Okay. Yes.
So you've used the 6 unison width thing two times, like a 1 is to homotope alpha
Right,
into
yes,
the
yeah.
center.
The first time I only needed 4r. The second time I really needed 6r,
I
right?
see.
And in fact, you don't need any of these constants. It's 2r, the real thing, right? But, okay. Right.
So where UIs intersect that segment, does it need to be the map F, capital F? Does it need to be 1-to-1 or something, or we don't?
No, we don't care. So the image, what we care about for my homotopy, what is important, right? So what was important for my homotopy is that when I take the image, so here you have V1, say here V2, the image will be something wild, but it lies in a simplex, right? In high-dimensional simplex, so I can homotopy. So it's a free homotopy, like going from simplex to simplex. Okay, maybe I should comment a bit on how this proof came about. So there was, I mean, somehow Guth proved a related conjecture of Gromov, and while he was doing that, he realized that what he needed, he made a conjecture that was actually about metric spaces. So Guth he made a conjecture about Burison content on metric spaces, which strongly indicated that, okay, what we are doing here doesn't require much the manifold thing, right? It's something purely metric. which generated somehow some new work. Well, in fact, Good's conjecture was proven by Rotman. Well, I guess I cannot write them. Nabutovsky, Lishak. Okay, I get the names. Lishak and Ljokumovic. But somehow more in the spirit of all proofs, and then there was another proof doing it in a more metric setting. And so I would emphasize that Guth, even though he's not directly involved, he played a role by somehow having this vision about metric spaces. And now let me first give you an outline of the proof. Basically, the proof has 2 steps, and then I will say a bit how the second step is proven. Okay. So before going to give the actual proof, probably next time, or I might start it this time. But so first of all, we have Karasev, right? Which I just proved, and I cheated. Instead of 2, I did 6. But anyway, we have so here, yeah. So here I only did 6, but okay. And then the second part is this, that the unison radius is less than this, which is less than this. Okay. And now combining the two, you get the function. Okay. So systole less than unison radius less than volume. This is my constant Cn, pretty much, right? Okay, so what remains to do to prove the theorem remains to do this, right? Okay, and now how do we do this? Well, it's going to be an inductive proof. So we're going to prove a somewhat more technical statement. So instead of focusing at R, we will assume that for every x there is a possibly different ball, because by the induction we won't be able to get always the same somehow radius, such that this inequality holds. Then the unison width is less than that. And now how do I know that? So this is the statement we will actually prove. And now how do I know I can start? How do I know this is true? Well, this is simply by taking R to be this number, then 2 to the R over n, and 2 R to the n over n factorial is exactly the volume. So certainly every x satisfies this. Just take R to be this, and then that satisfies it, right? So if I take R to be this, then the ball then then this quantity becomes equal to the volume, right? So if I take T equal to R, then this becomes equal to the volume, right? So certainly I have inequality, and you might complain I don't have strict inequality, but just take it R plus epsilon. Okay? So for some reason it's easier to work with strict inequality. Okay. So I think I started a bit later, so I have 5 minutes more. Okay, so now maybe before doing the calculations, I want to explain how do we prove that, right? So what is the idea?
So this idea of the star statement.
Right, yeah, so we want to prove this statement. So everything now boils down to this. We know that this condition is satisfied, I mean, at least when we're going to start, right? So we know that this is satisfied for Mn, right? I mean, the hypothesis. We know that this holds. So we want to show this, and I'm going to show it. Yeah, I'm going to explain how to show this statement star. Right? And it turns out we will prove it by induction, as I said. But let me. So the first thing is, as I said, I care about manifolds. But it turns out, as it happens often, right, that it's easier to prove something for a more general class of spaces, and we'll see why. So, and actually Gromov also had proven it for polyhedra, but for the proof we actually need to pass from manifolds to polyhedra, otherwise we cannot really do it. And we are going to do induction on dimension. So how we're going to do that? Well, we will show, okay, so how we're going to do it? We will start with a manifold, right? But the first step, we will start out with manifold, but the first step will be to take something of lower dimension inside the manifold and cut it in small pieces, right? And the problem is, of course, that there is no way to find something of lower dimension that is a manifold, so it's going to be a polyhedron, okay? So, so this is why my inductive step is actually formulated for polyhedron. So I'm trying to do induction. So given a polyhedron xn, I'm going, which has my property, right? So the balls have small volume. We're going to show that there is a subpolyhedron of dimension n minus 1, such that the connected components of this difference have small radius, and balls there have also small volume, right? So star is also satisfied. So just to say it explicitly here, star. So the hypothesis of star, right? The hypothesis of star holds also for this subpolyhedron. Okay? So we start, well, we have this, the connected components are small, and the subpolyhedron also satisfies my condition. So now I can apply induction, right? I can assume that this has small unison radius, okay? And now I claim that this, so now, okay, so first of all, how do we prove that there is such a nice subpolyhedron? Well, we try to kind of minimize overall, right? And we show that if we have a subpolyhedron that doesn't work, we can use the co-area inequality, cut and paste, and improve it. I will do that in detail, but we use cut and paste and the co-area inequality to show that there is such subpolyhedron. Okay, so just the co-area inequality. And then after I have done that, I can apply induction. I know that I have this thing that cuts, that has small unison radius. Well, this implies that xn has small unison radius. And maybe this I might even be able. This is now a simple argument. Any questions about the strategy? So this is the idea, right? And as I said, one of the difficulties is that we are forced to pass the polyhedra. Because if we try to cut a manifold like that, well, we'll get a polyhedron. We're not going to get, it's impossible to cut by a manifold. Okay? And this is, I think, somewhat nice, that you want to prove something for manifolds, but the easier way is to go to polyhedra. Okay, so maybe I will define, maybe I'll just define what are the subpolyhedron. So we say that the subpolyhedron is deseparating if each connected component is contained in a ball of radius r. Okay? Of the complement. And now, okay, there is one technical difficulty. I mean, you want to, say, go to a minimal site, as I said before, but there is no existence theorem for minimal subpolyhedra. You get nervous. Maybe as you go towards a minimal, things get strange and you don't see polyhedron anymore, right? Maybe one can show that such a minimal thing exists, but it would require a lot of work, and we only work with inequality, so we don't really care if something is minimal. Things still work as long as it is close to be minimal, and we can make it to be as close as we like, right? Okay, so we get all this polyhedron. Well, when we get close to the minimal possible volume, we stop. We say we are fine. Well, I mean, we have to pay a price for this, which is that we'll have to work with inequality. So this delta will keep bugging us through the proof, right? So, but, okay. And as I said, I mean, maybe I won't, actually, I might even prove that, and reprove it next time. So if I have this, and the unison radius of the polyhedron is less than t, then the unison radius, if the n minus 1 unison radius of the polyhedron is less than t, then the nth unison radius of x n plus 1 is also less where it's going to be. Okay, and the proof is very simple. So let's take the connected components. Now let's take a cover of yn with multiplicity n, right, with ready d, and now just thicken it this a bit and add the ui to get a cover of multiplicity n plus 1 of xn plus 1 with radii, well, almost the same, d plus epsilon. You don't care about this epsilon because you're going to take an inf. When you define the use and radius, you take an inf, so the epsilon comes for free. Okay, so this is actually also Karasev's simplification of some earlier proofs of this. And it shows how useful it is to move from one definition to the other definition, right? According to the situation. Okay, sorry.